myself out of had it. Okay, so right. So interactive oracle proof is a protocol between a prover and a verifier, where the prover sends messages, the verifier will usually send random challenges, and eventually, after many rounds, the verifier will either output accept or reject. So a polynomial interactive oracle proof is exactly that, except the messages specifically are polynomials. And so how do we get from this sort of theoretical object to a concrete, non-interactive, succinct snark? And that's through a multilinear polynomial commitment scheme. And so basically, or to be more specific, the messages are multilinear polynomials. And so the trick is that instead of sending a polynomial in full, you'll send something called a polynomial commitment. A polynomial commitment is a short message that represents a polynomial. And even though it's short and you can't really do anything with it, there is a protocol where a prover can then prove the opening, like an evaluation of the polynomial to the verifier. So basically, I'm a prover, I have a polynomial, I send you a commitment to it. The verifier sends me back an evaluation point of its choosing. I send back an evaluation of that polynomial at that point. And the verifier either accepts or rejects. So in this way, the verifier is able to obtain evaluations without knowing or needing to receive the entire polynomial. So essentially, in the polynomial interactive oracle proof, the prover is sending these very long polynomials, and we compile it to a snark by replacing those long polynomials with polynomial commitments. Does that make sense?
And are you going to say what security means for a PCS later? Or?
Yes, I think so. Hold on. No, I guess I end up describing the security of the scheme, but I don't think I described the general security, so I can spend some time on that now.
Well, yeah. So is it
Right.
what I would expect it to be of just for a random point, or is it for any point?
It's for any point, and yeah, so the two security definitions we want to satisfy are it's like a special type of snark. So we want completeness, meaning that if the evaluation is correct, the verifier will output accept, and then we want knowledge soundness, which means that there exists a polynomial time extractor that can extract a polynomial from the commitment that evaluates to the point that was approved by the verifier. Okay, that's kind of a hand-wavy notion of it. Hold on. So
so in particular, there's many polynomials that satisfy what you just said.
Yes, that's true. However, the commitment has to be bound to a unique polynomial. So there's a binding property. So yeah, exactly. So there's a binding property, and the prover needs to, there needs to exist an extractor that runs in polynomial time that can extract the unique polynomial from the commitment. That then also satisfies all of the claims.
Right, and I guess, right, such an extractor is obvious through multilinear interpolation, if I can.
Yeah, that's essentially what we do, but there's other ways to do it. Like if you ever read Solomon encoding, the extractor can just decode it and it will be a unique polynomial, or yeah.
When we say it's like short, like is it like logarithmic in the size of the polynomial or something?
Yeah, so in our setting it ends up being polylogarithmic. In the non-post-quantum settings, it can be like constant size. So short is also a little hand wavy. We try to make it as short as possible. Yeah, right. Okay, so right, so now I'm pretty much focusing on prover runtime here, and I'm going to describe why multilinear PIOPs are beneficial over univariate ones. So in industry right now, in the companies that have deployed snarks, they're all still using univariate polynomial commitment schemes, because that was what was fastest. And I mean, multilinear polynomials are pretty new. Commitment schemes, not the polynomials, are not new, but I think in the last 5 years, I think Spartan might have been the first paper to do that. I'm not sure. Don't quote me on that, but something around like 2020, I would say. So, okay, so multilinear PIOPs are beneficial because you're doing everything over the Boolean hypercube. So when you interpolate, evaluate over a Boolean hypercube, you're always just multiplying by ones and zeros, which is to say that you don't do any multiplications at all. So you're doing everything, it's just a finite field addition. For certain aspects of it, not for the entire protocol, but for certain parts of the protocol, you can get away with no multiplication. And the part of the protocol you get away with that is in the univariate setting would need to use a polynomial quotient, which it's the most efficient way to evaluate a polynomial, to compute a polynomial quotient is through FFTs. So basically we're able to replace n log n finite field multiplications with n log n finite field additions. And so that's like a huge benefit of using multilinear polynomials and PIOP. So for example, hyperplonk is a recent multilinear PIOP. And this is a comparison to jellyfish, which is a univariate plonk. This is from the hyperplonk paper. And as you can see, yeah, like the top rows, jellyfish wins. But as the circuit gets more and more complex, hyperplonk starts to win. And so a key use case of multilinear PIOPs is like what they call high degree circuits, where high degree gates, where you're like replacing many like high degree quotients with sum check and efficient operations like that.
And I'm sure you're going to get to this, but like sum check is not new.
Yeah,
right?
sum
Like,
check is not new.
Said multilinear polynomials are not new, right? Like
Right, yeah.
Like so
what was the key factor? Well, it's true. Even GKR, which is now starting to get super popular, was invented in 2008, and so it's also not new. And what is the key? I think the key thing is the efficiency of multilinear polynomial improvement schemes, maybe. Like, I think univariate PCS were the only efficient ones for a while. So like there were a lot of efforts to do univariate sum check, which isn't that as efficient, and try to make GKR work over that. That could be one reason. Another reason could just be that there's so much efforts in industry to make things super fast, and they realize that GKR is really fast for certain applications. But that's GKR. Yeah, sum check, I don't really know why history unfolded the way it did, because sum check is indeed super old. I think it's from 1990, right? Yeah.
Also, I guess like FFTs can be computed like locally, right? Whereas like the sum check protocol normally requires quite a bit of interaction. So is this like trading off the expensive FFT computation with more communication complexity?
That's a really good point. Kind of, but not really, because sum check ends up being done non-interactively, so it doesn't translate into communication, but it does translate into it. I mean, yeah, it is more like you have to do more of a Fiat-Shamir thing than you would with a quotient polynomial. Another benefit, actually, to be devil's advocate that I've heard from some industry people is that while computing a polynomial quotient is expensive, you end up doing it over a smaller field, because traditionally in Fry, you like do it over the base field and the challenges are from the extension field. So sum check runs over the challenges of sum check over the extension field. So you actually end up doing more operations over the extension field. I think the n log n multiplication should outweigh that, but maybe like, I don't know, when things start to get implemented, everything gets very unpredictable. So I'm not entirely sure. Like we need like a rigorous set of benchmarks to settle the score on this, but at least theoretically, like this should be faster, I think. Okay, so until recently, multilinear PCS options for them were limited. So there was like a fast group of them, such as Breakdown, which has a linear time prover, and like tensor IOPPs basically, but they have large communication, so like square root n communication. So then the most popular thing to do was to use Fry, but with this univariate to multilinear transformation, which has an overhead. And then also Fry has limited field choices. So these are the issues that we're addressing in this paper.
And sorry, if you assume for a second I don't know anything about polynomial, at least in the univariate case, can you like sketch me is the construction just coefficient G to the coefficients?
Like what does a univariate PCS look like? Yeah, the one that is usually used that's based on Fry is actually this is used, both the ones based on Fry and KZG, which is like a famous one. The idea is to use the idea that if f of v evaluates to h, for example, then the quotient f of v minus h over v minus h over v minus over x minus v. Hold on, no, I don't think so. Is a low degree polynomial as well. Maybe I can draw it on the whiteboard.
Do we have markers?
Here. Oh, okay. Yeah. So it's like, hold on. It's like if f of v is equal to h, then we create the polynomial f of x minus h over x minus v. Right, is a low degree. It's like this would also be a low degree polynomial, basically. I'm pretty sure that's the equation. It's like because basically you would say f of v minus h is 0.
Right, so that should have
v is
degree one less than the other.
Yeah, exactly. So v is a root of this. And so you can factor it out. Yeah, essentially. Factor out the x minus b term. Yeah, because then f of b minus h would be like, yeah.
And sorry to keep stopping you, but this just made me realize is that like the notion of hiding, do you still want some hiding? Right, because usually I do these queries over and over, like 1 point, second point, tell me what it evaluates to. So is what I want for hiding basically like the polynomial is just unknown up to it evaluates at these points?
Yeah, exactly. Actually, hiding is a little tricky with these coding-based schemes. But I think it is essentially hiding as long as you don't query so many points, as you said, that you can interpolate it. So as long as it stays information theoretically secure, I think it's okay. But yeah, a lot of these work, I mean, in BaseFold, we don't really address zero knowledge or hiding that much. But you can. I mean, I think you can mask the polynomial before you commit to it as well. I'm not sure. I think that there's some techniques that you can do. Like,
That's a reasonable definition. It's just,
yeah,
it's uniformly drawn from the, or like, it is simulatable up to
yeah,
having consistency with these points.
yeah, exactly. Okay, so anyway, though, for that, so what Fry would do, because it's a low degree test, is you would test that f is low degree, and then you would test this other polynomial is low degree, and crucially, you can derive the second one from the first one, like locally. Like if you have evaluations of the first one, you can obtain evaluations of the second one, because the verifier will have v and h. And then KZG does something similar, but with elliptic curve, or like with the knowledge of exponent. So it's, yeah, I don't know. I won't go into that because I don't know the details that well, but it uses the same fact. I mean, they're the one that I think originally used that as the thing. Okay, cool. So I'm going to talk a little bit about error correcting codes. So a linear error correcting code. Are you guys familiar with error correcting codes? Okay, cool. So linear error correcting code is just a k-dimensional subspace of f to the n, where k is smaller than n, so that you have some redundancy. It's over a finite field, which we'll refer to as the alphabet of the code. And then on this vector space, we impose a metric called the Hamming distance, which just says you have two vectors. The number of spots where they differ is their distance. So if you have two vectors that don't differ in many spots, then they're considered close. Otherwise, they're considered far. And we're constructing a proof of proximity, which enables a prover to convince a verifier that it knows a vector that is close in Hamming distance to a code word. So that is our goal.
Hadas?
Yeah.
Can I ask you a small question on the previous one?
Yeah.
On the previous slide?
This one?
Oh, yeah, here, right here. Yeah. So this is a correcting code or a detecting code?
I'm just describing an error correcting code, but I haven't described it. Yeah, this is general enough. But
Because
this is
how do you
actually
do correcting within this code? With a code which just satisfies this definition, how would you do correction?
You mean like how would you decode error correcting
How
code?
would you
Yeah.
correct? Right, because I can see this is an error detection code, but how would you do correction?
Oh, are
with
you
it?
saying that the definition is not specific enough?
Yeah, that's what I think, no?
Yeah. I don't have a minimum distance. Okay, well, I guess I meant to say that. So the second bullet point is saying this is the
Oh, the
definition
second
of
bullet
Hamming
point is
distance.
fine. The Hamming distance is fine, of course, no problem with that. I was just talking about the fact that you said this is
Yeah.
error.
No, you're right. It's not specific enough. I should say in the first bullet point, like that has a minimum distance that is like suitable.
Ah, okay. So you want to have
Yeah.
a minimum distance, and then you can use it for error correction. Makes sense.
Yeah,
Okay, fine.
exactly.
Thank you. Thank you.
No, thank you.
That's fine.
Thank you. I'll update the slides for future talks. That's helpful.
Thank you.
Yeah, thank you. Okay, so now Fry is a popular proof of proximity because it sort of has the best trade-off between prover and verifier in the sense that the prover is quasi-linear and is concretely pretty fast, and the verifier is polylogarithmic. So that's good. So basically, the way it uses a split and fold approach, which is a thing that's used across protocols, and the idea is that in each round, the prover sends an oracle to a code word that is half the size of the oracle from the previous round. So eventually, after d rounds, you get a constant size vector, which it can read in full, and then it will conduct a series of proximity tests to make sure that each round is consistent with the last. And then you can believe that the original oracle is sufficiently close to your code. Now, actually, in practice, you don't actually want to send something that's half the size of the oracle. It'll be some fraction of the size of the oracle, and you can like sort of find the best parameter for that. and skipping rounds and all of that. But yeah, but this is sort of like the simplest way to describe it.
And when you say oracle to code word, you mean a polynomial commit.
So so the original thing is sort of the commitment. And this is in the interactive setting, like it will be compiled with a Merkle tree eventually. So you'll end up just sending Merkle roots to these things. But now we're just in the theoretical, magical world where we're sending things to.
What's an oracle to a code word?
Yeah, it's just, I mean, it's just it's actually just, yeah, it's just a vector, but we just like imagine that it's like a thing that can be queried and that you can return elements of. But actually, it's just, yeah, the idea is that just like I am an oracle to a code word, that means that you as a verifier can query and ask me to send you like different elements. Yeah, it's fixed, yeah. But in actuality, it's a vector that is then committed using a Merkle tree. Right. Okay. So how do we do this in linear time though? So this is like a cool thing about Fry is that you don't actually have to encode everything from scratch when you do each subsequent oracle. Instead, what you do is because of the structure of Reed-Solomon codes, you can do this cool thing where you take the vector, you split it up into pairs, and then each pair you interpolate on like specific points related to the code. You evaluate it at the verifier's random challenge or at any point, and it happens to be equal to the encoding of the linear combination of the right plus the left, like the left plus the right. And so that just has to do with the structure of Reed-Solomon codes. But essentially, and I'm going to explain that more later, but this is like a key point of Fry that you don't, although interestingly, there's recent work, Stir and Whir, that you may have heard of, where they actually do encode everything from scratch, sort of like taking us back to, because they encode it with a code word with a smaller rate and better distance, and that way, and that's how they like lower the communication complexity. But in order to do that without blowing up the prover time, they have to do, they have to not just do it 1/2 the size, like they're sending something that's like 1/8 of the size, and then they're re-encoding it. So they're still using the n log n, but it ends up working out because they're doing it on sufficiently smaller code words. That's an aside, but kind of interesting because it's sort of the key property of Fry. Okay, so now that was sort of introduction, and I'm going to go into the contributions of BaseFold. So starting with foldable codes, which is showing how we generalize Reed-Solomon codes. And I'll get more into the structure I just showed as we go. Then random foldable codes, and then finally multilinear PCS construction from foldable codes. Okay, so another fact about linear codes I didn't mention before is that you can always write them in terms of a generator matrix G. So an encoding of V is always V times D. So we define foldable codes to have a matrix, to be a matrix with this nice recursive structure where GD minus 1 is a generator matrix of the previous code, which you can think of as it's a code with half the message size, like the message length and the block length are half the size of this new code. And TD are diagonal matrices. So the TD and T prime D are diagonal matrices. So this is a recursive construction. So like this is a generator matrix of the code CD. And then CD minus 1 would have a similar structure with different diagonal matrices. So basically, a foldable code family can be defined by this set of pairs of diagonal matrices. Okay, so I'm going to motivate this now because
we don't mind if the T's change along during the cascade, or the T's want to be the same structure every time. So it's always like a tensor product of the original matrix with some little TD product.
Yeah, they're fixed for the whole code. Yeah, they're fixed. They're like, you could think of like usually you would define a code by its generator matrix. In our case, we can just define it by these diagonal matrices, and then you can always build the generator matrix from them. But yeah, exactly right. It's a tensor-like sort of thing. Okay, so starting point, viewing Reed-Solomon codes over FFT-friendly fields as a foldable code. So this is the motivation behind this design was sort of pulling the structure out of there. So okay, Reed-Solomon code, the generator matrix is a van der Waals matrix. Each column is identified with a point, and each row is a degree, or like a power. And then if you do the vector times the matrix, the idea is that you end up with the evaluation of a multilinear polynomial over this domain. Okay, so I'm going to show you why it's the structure. Okay, so first we're over a cyclic group. So a cyclic group is a set of elements where every element is the power of some generator element, right? So if we just replace the matrix from the previous slide with the powers of these of this generator element in the cyclic group, you get something that looks like this. And then multiplying out all the exponents and, converting 1 to 2 to the 0, we get this matrix. And so as you can see, the even rows, if you index from 0, so 0, 2. So the even rows, you can see they have this mirror structure. So you can see the left and the right are identical. And so that matrix, as you can see, this is the matrix that's on both the left and the right. This is going to be GD minus 1. That's what we call GD minus 1. And now going to the odd rows, you can see that all of the odd rows are the element above it times something that is constant to the column. And so that's where we get the diagonal matrix from. So you can pull the diagonal matrix out of that, and you can see that the odd rows are actually equal to GD minus 1, this green matrix, times this diagonal matrix. Are there any questions?
And you didn't, right, the choice of G here, like, there's just some G.
Yeah.
that causes this to happen.
Yeah, exactly.
And then at the end, are we going to want a group that's like a power of 2 or something? So we
Right.
can repeat this.
So yes,
The whole cascaded set of code.
exactly. So traditionally, that is what an FFT friendly field, that's how it's defined. So that there's a cyclic group that's a power of 2. So you always have to pick a finite field whose like multiplicative cyclic group, or like it contains a subgroup that is sufficiently large and a power of 2. And so one of the motivations of this work is to like get away from that. And so I think that, right, so that's where we get to random foldable codes, where what we do is we sort of make a contrived version of the structure by sampling the TDs randomly. So like basically the key insight here is that, yeah, usually to algebraically get this structure, you are right, the cyclic group has to have a certain form. But we can, because the structure just ends up being that, it can be totally defined in terms of matrix multiplications, and the only requirement is that the TDs are diagonal, then, you can make the TDs any diagonal matrix and still get that structure. Now, you can't make the TDs anything and still get good distance. So we sample the T's randomly, and we prove that it has good distance. Yeah, so that's the next part. But before I go there, are there any other questions on this part?
It just, right, you have a similar, I guess for BCH, it's in your window. Sorry.
Yeah, it's and this does look a lot like a tensor code. It's kind of like it's like a tensor code, but in each round, it's like it's like a many UIs tensor. So a tensor code is where you encode the rows and then you encode the columns. All right, so this is like if you repeated that many times. However, you don't, like your code is, you're like puncturing it at every turn. So like, I can't get into that now, but I've written this out before, but I don't have it on the top of my head. But basically, this is like this is some sort of a punctured tensor code. So, yeah. Okay, so random foldable codes. So right, so in a random foldable code, we sample the TD and TD prime randomly. And
Before you go on, just
Yeah.
sorry, keeping up with you. And in the algebraic setting,
Mhm.
where you have the luxury of doing all of this inside of whatever a group of, order 2 to the K, then you get the coding properties you want just because the determinant of the van der Waals matrix is under control, and you can do it all algebraically, and it's great.
exactly.
So now you want to step away from that, and now you're going to have to do some more work because you're going to pick the TDs at random.
Exactly. Yeah, initially when I saw this, I kind of naively was hopeful that like it's the structure that brings the distance, but it's not. Like the Reed-Solomon, it's properties of polynomials that bring Reed-Solomon distance. So yeah, but we ended up getting good distance. It was more complicated than I had hoped it would be, but it ended up being okay. I mean, it's now a random code, which has some disadvantages. So the distance is probabilistic, but we show that with like with overwhelming probability, it has good distance. It is dependent on, but I'll get into it. Okay, so I'm trying to give like a high level overview of the distance argument. So it's a recursive argument, or an inductive proof. So imagine that we are trying to prove the distance of CI plus 1. So we have 2 vectors or 2 code words from CI, And let's say that we already know that CI has good distance because it's an inductive proof. So to construct our new code word, it's going to look like this, where the circle is the Hadamard product, where it's component wise multiplication. And this is just, and the TI is the vector of the diagonal matrix TI. So it's just the vector of the diagonal. You can show yourself, you can write this out and show that that's what it ends up being if you were to multiply the vector by the recursive generator matrix. So you get VL plus TI Hadamard VR, concat VL plus TI prime Hadamard VR. And so the jth element will be VLJ plus TIJ times VRJ. And the J plus N over 2th element, where N is the length of the code word, will be VL plus TI prime J times VRJ. Okay, so we want to analyze how many, because it's a linear code, we can just analyze how many zeros there will be in this new thing, right? So the first thing we do is we identify this polynomial. For each j, there's this polynomial VLJ plus x VRJ, and essentially then the new VJ is that evaluated at one of the t's, and then the other one is that evaluated at the other point. So Px is or P, the polynomial, sorry, that should say Pj. Pj is univariate polynomial of degree 1, so it only has 1 0. And then since Ti is sampled uniformly, this is basically a Bernoulli trial. So you can think of like you're flipping f, the field size die, you get a value, and you test if it is a 0 of this polynomial, and it will be with probability 1 over f, something like that. And so each of these is a Bernoulli trial. And so what we want to do is analyze the probability that like more than x of these are 0. And so we use a CDF of the binomial distribution to do that. So it's just basic probability. Okay, except for one thing I didn't mention, which is that we don't know where actually VLJ and VRJ are both 0. So what I said is true as long as they're not both 0. Okay, if they're both non-zero, then what I said is true. If only one is non-zero, it's even better because there's no way that it will be 0. Or VLJ is non-zero, I guess. However, if both are 0, then it's definitely 0, right? So the key idea here is that let's say you have a code word that is already 0, has coincidental zeros at many points. You do not want to be analyzing that in the same way as you're analyzing a code word that has no zeros at any points, because the one that already has zeros is sort of already done. Like you're not going to get a good distance from that. So what we do is we partition the code words. And very luckily, okay, so we partition the code words into these sets. Si, as all the code words with zeros on the set I. Now, very luckily, as I gets bigger, the number of polynomials with zeros on that set gets smaller. And we end up proving that with the rank nullity theorem. I won't get into that now, but just believe me that that's true. So because of that, now for each I, we take the union bound over all the polynomials in Si, and we multiply it by the term given by the CDF of the binomial distribution. And so essentially, as this union bound, as I gets bigger, the size of Si gets smaller, and then the term given by the CDF of the binomial distribution will be different because, like, okay, let's say we want to prove that there are no more than x zeros, right? Let's say we are on a set I that already has x minus 1 elements. So we're already considering that this polynomial already has x minus 1 zeros. So now our CDF is just the probability of there being one more 0, which is low. That's like 1 over f. Now let's say we have a code word that has no coincidental zeros. Then the size of Si will be huge. Actually, most code words don't have zeros coincidentally. But the term in the CDF will be a larger probability because now it's way more trials, essentially, and way more successes that we're expecting. So this ends up working out because of that pattern. Does that make sense? Sorry, I know it's a dense slide. Are there any questions?
So just to say it back to you, so like large subsets, the chance of them all being 0 is very small, but the number of extra trials can be big, but that's fine. And then small subsets, right? Like you have to have, so small subsets you need.
I think it's a little bit I think if you switch up small and big, then what you said is correct. So basically, when I is big, that means that VL and VJ have many zeros at the same places. Okay, there are not many code words that satisfy that. And you can just prove that through the rank nullity theorem and using the distance. Okay, so there's not many polynomials that satisfy that. And so let's say there's like, yeah, so there's a few of those. And if we're only aiming for X zeros, let's say they already have a lot of zeros. So now the CDF will be, what's the probability of one success out of like out of whatever many trials. So yeah, basically as this term gets bigger, the other one gets smaller and ends up balancing each other. Okay, so I took this out from the paper and circled. This is basically what the proof of the distance says. So the probability that there exists a message such that the number of the zeros of the encodings is greater than TD. And then here, this is the CDF of the binomial distribution. And then we split it up into sets. And basically that ends up being the size of the number of polynomials that are 0 on a set F. So yeah, so that's how the distance works out. And then here are the concrete parameters. So it's dependent on the field size. So as you get a larger field, the distance is better. So for example, for this last entry, that's actually near the singleton bound. I think the best a distance can be for that rate. Now it's not as good if you have smaller fields. You can do a trick where you start with like a good base code that slows it down a little bit. But if you, for example, use Reed-Solomon code for the first few rounds, you get a better distance. So these are the distances you get, which.
Sorry, can you rejection sample? Like, can you actually check if your TIs are good?
I don't know. Maybe. That would be interesting. Yeah, I haven't thought about that.
Because presumably, like, you're using Reed-Solomon for good distance properties at the beginning.
Yeah, right. Yeah. Yeah. Yeah, I think you could rejection sample. I think I think you could also test the code probabilistically, even though it's very big. But I think you get some guarantee that way too. There's also distance boosting techniques, I think, that people use in coding theory. I haven't explored. Yeah. Okay, cool. So I don't know how I am on time. Okay, cool. Are there any questions before I go to the next section? I'm sorry, that was a mouthful.
So I guess before you go on to PCS, like, do you see, right, obviously you don't know anything about, or let me check, you don't know anything about efficient decoding here.
Yeah, we don't. Right. So we get what we do, we build like a special knowledge extractor that doesn't use a decoder for this. And so it's not a straight line extractor anymore, and that's one disadvantage.
But can you think of application, or like, are there other applications where this would be better than like a random linear code? Or is
yeah, I guess why is it better than a random linear code is that the encoding time is quasi-linear, which a random linear code, it will always be quadratic, I think. And yeah, I mean, its distance properties aren't quite as good. Another way to think of it is actually one of the motivations for the work too is a line by Guruswamy on randomly punctured Reed-Muller codes. So I think he proved that randomly punctured Reed-Muller codes look similar to random codes. And so in this case, we just puncture it in a specific way. Like that's another way to view these codes is that you're just puncturing it along this kind of foldable domain that's easy to do proximity tests and encoding with. And then because we're not randomly puncturing it completely, you lose some of the distance, but you gain some of the efficiency.
So maybe I missed it. So is it easy to say what, for example, the expected distance is that you get out of the construction?
It's not easy to say it in terms of like an equation, because we have an equation for it. It looks something like that if you like plug all the things in, but I basically use Maple and just calculated it. So we do have a equation, but it's not super pretty to look at. But these are the concrete bounds we got from computing it on a computer.
I see. I mean, but maybe just like some asymptotic. I mean, so for example, does it with high probability, does it give you something with constant fraction distance?
Yeah, okay. Okay, the problem is, yes, however, not for many, like, I guess to say it's an asymptotically good code, for example, we can't actually say that because as the block length increases, the number of rounds of recursion increase. And every time you do a round of recursion, you lose some distance. So if you were to like put it to infinity, it's eventually the distance will go to 0. But for the sizes we care about for snarks, it ends up being like concretely good.
Okay, I see. Okay, I see. So
Yeah.
you lose a constant fraction for each layer of the construction.
Yeah,
So what if you increase the sizes of the T matrices so that they're log, instead of just constant size objects, what if they're log size objects? Then can you drive the loss per round to something, you know, asymptotically 1 minus 1 over log so that you get an asymptotically good family of cut?
maybe, but the T's are already the length of the block length of each. Like the diagonal, it's equal to the, wait. Yeah, I think it's equal to the block length of the code that you're in. So like you start, it's a family of codes, right? So you start with a constant size code, and then the T of that round is constant size, but then you double the size of the code in the next round, and then the T is double the size. Is that in line with what you were thinking?
Like, can you
If you increase T, yeah, that's a good point. You probably, yeah, I think that would, yeah, maybe that would work. I never thought about that.
Okay,
So
that'd be
thank,
exciting.
that would be good.
Yeah,
Yeah,
exciting thing to say.
yeah,
It's like a nice message.
yeah, yeah, that's interesting. So yeah, this is where the loss happens basically is with the probability. So like each round you are, yeah, you're stuck with the, yeah, like I guess it's a CDF of binomial distribution. So you're always, you have to allow for some loss in each round where like there's successful trials of finding zeros. And, but yeah, that's a really good point. I would love to talk to you about that more. That sounds really cool. Yeah, I think you could get you could maybe get an asymptotically good family of codes, then you would lose maybe some of the efficiency because T would be larger.
Yeah,
But
no, understood.
yeah, but that another thing I want to try because I learned afterwards about all these distance boosting techniques people use, like where you can pack, I don't know, elements together and do it over a different alphabet and things like that. So I don't know. That would be beneficial.
By the way, do you know, I mean, is there a direct, yeah, so is there a way that you know of to algebraically choose the T's? Okay, so obviously I know the answer is yes, because one thing you can do, of course, is that you can just recreate the construction of a group with size like 2 to the k.
Yeah.
So I know there's an algebraic setting that does this, but I mean, I guess what I have in mind is if you think about how a zigzag construction works. Right? The zigzag construction is you take the thing that worked, you tensored it with this small object, and then you get a new expander graph at the next.
Right.
And they are able, and I forget the details, basically to show that as long as the thing that you tensor with has some good properties, then the construction has some good properties. So anyway, it just seems like it would be super sweet if you could formulate some properties of the T structure so that you guarantee that you lift good distance to good distance, but maybe that's hard.
Oh, that's a good idea. Yeah, that's true. I'll think about that more. That seems like it should be possible. Yeah. Yeah, I think there's other things you can do for sure now. Yeah, the zigzag construction and that stuff I've been reading about recently. That's super, yeah, fascinating to do that. Okay, cool. So now we're kind of changing gears completely. This is the other contribution of BaseFold. Sometimes I think these two things shouldn't have been in one paper because it's a lot. But yeah, so this is a PCS construction from foldable codes. And so this can be used with Fry. So basically this is what made Fry to be able to directly be a multilinear PCS. Okay, so the key thing now is like we're going to view any foldable code as a punctured Reed-Muller code, as I was saying. So Reed-Muller codes are evaluations of multilinear polynomials. So this code are multilinear polynomial evaluations over a certain nice domain. Okay, so just to prove that to you, it's like an inductive proof. Assume that ML times GD minus 1 is the evaluations of a multilinear polynomial whose coefficients are ML. Like ML is a vector of coefficients. Then if you multiply all this out, you get ML times GD minus 1 plus P times MR times GD minus 1, which which is the definition, by the definition of multilinear polynomials. This is a new multilinear polynomial of double the number of coefficients and one more variable and evaluated at that t. So because of that, this ends up being evaluations of a multilinear polynomial.
And the number of variables in it has to do with the number of layers of your construction.
Exactly. Yeah, exactly.
I see, which is sort of interesting because it's like then you have the number of variables is like log the total dimension of the total size of the code.
Yeah, exactly. It goes back to also the tensor. I guess if you view multilinear polynomials as a tensor code themselves, then it's like every layer of tensoring is one more variable. Okay, so then this is the domain. This is like what the domain looks like if you write it out in variables of our multilinear polynomial. So you can see there's like a repetition pattern. So this is like x1, y1, z1, x2, y2, z2, x1, y3, z2. So, okay, so the first thing you would do is like you would end up from your first round with univariate polynomials evaluated at x1 and x2. Okay, then you pair them up. You take your two polynomials evaluated at x1 and you then evaluate them at y1. So basically, right, you'd have like, before I had the notation PL and PR. So it's like PL evaluated at x1, PR evaluated at x1, and then you get a new polynomial PL of x1 plus y1 times PR at x1. And so you get the new evaluation that way. Okay, so now going back to, this is a different description of the Frye opening phase I was talking about. So, if you recall, you have a code word, you split them up into pairs. So in this case, the pairs are these two evaluations, x1, y1, z1, and x1, y1, z5. You can see then that you can view this as a univariate polynomial evaluated at two different points. So you interpolate them at z1 and z5, and then you evaluate them at the verifier challenge, and you end up with this thing down here. So PL plus RPR evaluated at x1, y1. And so essentially what you do is you swap out the z variable for r. And so now we have we've reduced it down because we have a lower degree, or a polynomial of one less variable, and evaluated on a different domain, which is the subdomain here, and it is equal to PL plus R times PR. And the key point here is that at the end of all of these rounds, you end up with a random evaluation of a polynomial. So the key point here is that a Frye proximity test, or our generalization of the Frye proximity test, doubles as an evaluation proof at a random point. So it is in itself a PCS, a polynomial equipment scheme, but only for random points, because it ends up being evaluated at the verifier challenges of this interactive proof. Does that make sense? Or are there any questions? Yeah, I think. Okay, so that's the key point. And so then once we have that insight, we take, as we were saying, the famous sum check protocol, which allows you to evaluate a polynomial using an interactive proof that actually follows the same structure as the proximity test. And in the end, you can complete the proof simply by getting a proof of evaluation of the polynomial, which was committed to at a random point. So usually this has often been used, and usually what you'll do is afterwards you'll run another polynomial equipment scheme at the random point. So basically, to do a polynomial equipment scheme, you always have to then do another one, but at a random point, because the sum check is for the sake of doing this at like a non-random arbitrary point, right? So our strategy here is that you interleave the two things. So you interleave sum check with the proximity test with shared verifier randomness. And at the end, you need to evaluate this at a random point, and now you already have it for free, basically. It's the last oracle of the proximity test. Right, okay, so we prove knowledge soundness. We have to prove that there exists a polynomial time extractor with black box access to the prover that can output the underlying polynomial that satisfies all the checks. So for the Reed-Solomon code, the knowledge extractor can just query sufficiently many locations from the Merkle tree and decode it using a Reed-Solomon decoder. For random foldable codes, we don't have a decoder. So what we do is what I think you said earlier, you run it many times until you can interpolate the polynomial. So we have a proof that, like with high probability, the extractor will be sending random points. With high probability, each one is correct, and then you just interpolate it. And so, okay, a key challenge with BaseFold was that in Fry, the last oracle is just an artifact you can throw away. The only point of it is that if it is a code word, then the first oracle is a code word. But in BaseFold, you have this extra burden of proving that the last oracle is actually an evaluation of something that is close to the original oracle. What we want is like something in the list decoding radius. So until recently, in the original BaseFold paper, we could only prove this in the unique decoding radius, whereas Fry uses the list, like check, basically the Fry verifier can check in many fewer locations than what the BaseFold verifier could check in. However, luckily, recently, there were two concurrent works. One was mine that proved it in the double Johnson bound, which is like the square root of the list decoding radius. And then there was another one by Ulrich Habach, who proved it in the list decoding regime for Reed-Solomon codes, which is, yeah. So my thing was general to any linear code, but has a slightly worse bound in terms of how many queries the verifier needs to make. And then Ulrich proved it with like the best possible bound so that it matches Fry completely, but only over Reed-Solomon codes. So that's good because BaseFold had like really bad communication until these results because the verifier had to check it that it's so much closer. So you have to query so many more times. So the benchmarks that we have is that it's 2 to 3 times faster than prior multilinear PCS. And then it turns out that it doesn't require polynomial quotients, has turned out to be useful in other scenarios. Like, for example, there's a paper called Binius, which does like Fry over binary fields and shows some efficiency there. And their trick doesn't work if there's polynomial quotients. So they use BaseFold. And then I think in recursive settings, it's useful. So it's more useful, I guess, in the 2 to 3 times speed up. The verifier is better than breakdowns, which is another field agnostic code that has a better, faster prover time. The field agnosticity allows you to do certain applications. For example, like anything involving an elliptic curve that is over a certain field that isn't FFT friendly, you can now do that. And that ends up being a lot faster because you don't have the constant overhead of modular multiplication. So for example, these are benchmarks for ECDSA circuit. So we have a much faster prover than Fry and KCG, and then like better verifier time than breakdown. Yeah, and then these are some charts showing the prover time. I think the benchmarks could be better, and there are some new implementations actually of BaseFold. I think the company Scroll has a new open source implementation, and yeah. So future work, I would like to explore more practical applications of field agnosticity. Now that I've proven BaseFold in the double Johnson bound, it'd be cool to prove it in what's called the 1.5 Johnson bound, which is something that Fry has been proven in. There's a paper called Deep Fry that does this, so that'd be cool to extend it. And then prove better bounds on the distance of the random foldable code, which you've given great suggestions for, so thank you. Yeah, and that's the end of the presentation. So thank you for listening. We have time for questions.
Was it flat?
Oh, okay. So do you, is it possible to characterize So what about the Reed-Solomon? What, sorry, how, let me start a question 4 times. So, right, or normal Reed-Solomon decoding is doing those polynomial quotients, but it's, so assume for a second that you're in a field that is friendly to those. Do you have a sense of what type of T is going to admit similar decoding techniques?
No, I guess I don't. I haven't thought too much about that, but I guess it would have to be, I think, an explicit rather than a random code for any kind of decoding to work, maybe? Not sure. Is there any random codes that you can decode? I guess it could. I guess you could. I
My
guess
question
it's
is,
not
like, what's the
contradictory.
structure that,
Ah,
right, like you're, obviously I need to be able to do polynomial division, fine,
yeah.
but T's not affecting my ability to do polynomial division.
Yeah, that's true. Ah, right. But I guess I haven't looked closely at this, but when I tried to, I think my co-authors and I tried to decode this like briefly. But if you just do, but I guess I'm not that familiar with the Reed-Solomon decoder, honestly, so I can't really speak to that. But if you just try to do like polynomial interpolation, it doesn't work because, yeah. But how does the Reed-Solomon decoder work actually?
Well, so
But it uses.
so Alex and I have this running joke.
Okay.
Every 6 months, we have to re-explain Berle-Campbell.
Okay, yeah.
They're always like, yeah, I have to devise some error locator polynomial.
Yeah.
So, like, the basic thing is that the total number of points you have, the product of the original polynomial, and like a polynomial that just has zeros at the errors, that thing, it has the degree of the total number of things that you've seen.
Okay, I haven't tried to do this. Maybe it's possible to apply something like Berle-Campbell, although maybe not, because if you try to, I mean, just intuitively, the distance proof of Reed-Solomon cannot really be used with these T's at all because you don't have the properties of univariate polynomials. So Berle-Campbell probably heavily relies on univariate polynomial properties, no?
Although, I mean, maybe it's kind of worth
Investigating.
here because I think that the proof that you can do list decoding for Reed-Solomon, my memory is that proof looks just like the Berle-Campbell decoder, but with multivariate polynomial, with bivariate polynomial.
Interesting.
And I kind of forget now the details, but yeah, maybe it would be kind of worth exploring a little bit because that would be
That'd
really
be
exciting.
awesome. Yeah. Okay. Thanks. Yeah, I will explore that.
Well, it's, I guess the last, it is the way that Berle-Campbell is it proceeds with a decreasing number of errors, right? Until you get like a polynomial division that's equal to 0. And then it's like, oh, that must be, so you're assuming the largest number of errors, waiting for a quotient that's 0. So you can't, right, so there certainly would be an overdetermined system at some point if you have too many errors. But yeah, I don't remember how list decoding.
Yeah, I think I could recover that. Yeah, but I mean, it looks just like, I mean, my memory is it looks just like the Berle-Campbell proof with bivariate polynomials instead of univariate polynomials.
That's really interesting.
And by the way, I mean, it sounded like, maybe it's obvious, but it sounded like at the end of the day, the code that you have is a punctured Reed-Muller code.
Yeah.
Right. So, I mean, I guess the other thing to ask, and I mean, here it's really outside my familiarity. I mean, I think a lot is known about decoding Reed-Muller codes.
Yeah.
And I wonder if there is a Reed-Muller decoder that has the same structure that you want. Right.
That would be really
Honestly,
cool to see.
I don't know much about efficient decoding.
I've said Reed-Muller it's just multivariate. It's general to multivariate polynomials, right? Okay, so I think what I've seen so far and things I've tried is that multilinear polynomials seem to like lose all the structure you get from other things. Like things don't work as well over multilinear polynomials, and then the puncturing also ruins a lot of structure. Like I guess Reed-Muller over multilinear polynomials is usually defined over the entire field,
Yeah.
and f to the n, and then you know a lot of things about it. And as soon as you start puncturing, you lose a lot of information. So far, I've sort of always reached a dead end when I've tried things, but I've never tried looking at that. So that could be interesting. Or maybe actually one thing I tried for a bit with somebody was trying to structure the t's a little differently so that it actually was maybe like a multivariate instead of a multilinear polynomial coming out of it. And it didn't, and we were trying to increase make the distance better, and that didn't work. But maybe doing that would allow something like Berlekamp-Welch to be applied. I don't know.
And as far as you know, there isn't, I mean, this doesn't end up being just like a subspace code. The puncturing is more complicated. I mean,
Yeah.
puncturing is, the structure of the puncturing is much more complicated than something like
Yeah. Because, well, yeah, or maybe less I don't know. Yeah, different. It's not algebraic at all, I guess. It's just trying to follow along to make it efficient in like a purely linear algebraic way. So there's no like structure to it, which is another disadvantage. But yeah, I think that's yeah, you guys have given me a lot to think about. Like maybe revisiting, as you said, like I think there is a way to structure T's to get more things out of it. I've only tried to do it to increase the distance and that didn't work, but maybe other things would work. Cause yeah, I think.
Also, first time I saw this, I was thinking because you're dealing with list decoding and multilinear thing. How does it work if we use folded Reed-Solomon code that is just having a tuple for each code symbol rather than like
By around
yeah
1/3.
having a larger code blocks, so we mix each like M code symbol together and make it to be one symbol, so we boost the distance.
Oh, that's really cool. That's what a folded Reed-Solomon code is? Okay,
Yeah.
I've seen folded Reed-Solomon codes and I never knew what they were. That's
So
interesting.
that's how they boost the distance.
Oh, okay. That could work to boost the distance, yeah.
Well, just since I know we have a faculty meeting about to start, why don't we say thank you?
Okay. Thank you, guys.
Sure, we can keep you going all day, but we don't.